To go back and now review some things that we already know and just look at them in the context of particles as waves. And in particular, let's just remember that we studied waves, and when we studied waves, right, we had a wave function, which a sine kx minus omega t for a single frequency wave. And then we did complex waves and wave packets, right? We talked about a wave packet, and that is when you add up different wave functions, right? So we can put subscripts on these things, right? Where A is the amplitude, K is the wave number, omega is the angular frequency. And so we can sum up the wave functions of individual frequency waves. Sorry, the squeaky chair. That's my chair. And so that gives us wave packets, and we talked about the envelopes and how we isolate a single packet. And what we're going to see in quantum mechanics is that we can treat a particle as a single wave packet. So let's talk a little bit more about these things. So let's remember that for a wave, E equals hf is the energy of a wave with frequency f. And the de Broglie wavelength, which came from Einstein, an analysis of the momentum energy relationship for relativistic particle. That's where this ended up actually coming from. And also remember, we talked about for a wave packet, there's a phase velocity, which is omega over k, and then there was the group velocity. The group velocity. This is all stuff we did before, which was d omega dk. Omega, remember that omega is 2 pi f, it's just the angular frequency, and k is 2 pi over wavelength, it's the wave number. And so you should be able to see that the group velocity can also be written as dE dP, since dE is hf, right? d hf, and dP is dh over lambda, by both top and bottom by 2 pi, so that's dh 2 pi f over d. This is a derivative, but anyway, h 2 pi over lambda, then that's the same as d omega dk. Okay, so dE dP. V group is dE dP. So that's true for a wave. Now let's see how that works out for a particle. To a relativistic particle, right? But relativistic is the most general we can get because that just simplifies to non-relativistic if we're not at high speeds. And remember that Einstein said E squared equals P squared C squared plus M squared C to the fourth. So let's go ahead and take dE dP. Therefore, dE dP is equal to, therefore, if I want to take dE dP and take the derivative of the equation above, it's going to be 2E dE dP is equal to 2P C squared dP. And this goes to 0 when I take the derivative. So that's just taking the differential of both sides, right? We're just taking the differential of both sides. Screw that up completely. So if you take the differential of both sides, we're just taking the, there we go, 2E dE equals 2P dP C squared. Okay, and so therefore, or take the square root and take the derivative, but this is the quickest way to take the derivative. I am simply taking the derivative of dE dP in case you don't see the math. You can go ahead and take the derivative of E with respect to B from this equation, and what you will find is that solving the equation above, dE dP is equal to 2P C squared over 2E. I think that's right. Doing this relativistically, so the 2's cancel. P is gamma mv. We got the c squared still. And E is gamma mc squared. So we get that. And so what's left? We have a gamma mc squared on top and a gamma mc squared on the bottom. Oh my gosh, what do we get? We get dE dP is v. What was v? V was the velocity of the particle. So remember when we said, okay, so whoops, using these relationships that I put in the lower left-hand corner for a relativistic particle of mass m moving at speed v, and what we get is that if we apply the group velocity for a wave to that using the de Broglie wavelength here, we had to use that over here somewhere, what you get is dE dP, the group velocity, is just the velocity of the particle. Whew, that makes sense, right? The group velocity, if a particle is being represented by a wave packet, the velocity of the wave packet is a measure of how, that's the group velocity. The group velocity is the velocity of a wave packet, right, of the envelope term. And the velocity of the envelope term better be the velocity of the particle if it's representing a particle. So we've just shown that. That's great. Better, non-relativistically, simplify as well. So we can actually just go ahead and redo that non-relativistically. Non-relativistically, E equals P squared over 2M. Again, V group is still dE dP. And now it's easy, right? dE dP is 2P over 2M, which is 2mv over 2m, which is V. V group is equal to V. So, that again, if we've got a wave packet, and we're saying that that wave packet represents a particle, the wave packet moves at V group, the particle moves at V. Those are the same thing. An example of a wave packet. We had so far, this is not the Gaussian wave packet. Right? I'm just going to say, again, remind you that we had written down a single frequency wave sine kx plus omega t, and then we had said you can sum up single frequency waves by varying the various k's and omegas and even amplitudes, and to make wave packets. And we had really only summed two of these. And when we summed two of these, we had done an example where A1 equals A2, but K1 not necessarily equal to K2, omega 1 not necessarily equal to omega 2. And we used that as an example of a wave packet, and then showed with the simulation that if you add in more components, you can localize the wave packet better. The Gaussian wave packet is an example of a localized wave packet. So that was just, a reminder of what we had done before. But the Gaussian wave packet is an example of a localized wave packet. The Gaussian wave packet is represented by this function. It's an example of the spatial dependence. This is just the spatial dependence. We've taken off the time dependence. Spatial dependence. Taken off the time dependence. Just in space, what does the Gaussian wave packet look like? The Gaussian wave packet is a way of summing an infinite sum of single frequency waves to get it's a Gaussian distribution of single frequency waves that gives you this infinite sum that ends up being the function that I've written here. So this is our Gaussian, what's called the Gaussian wave packet. Again, it's the spatial dependence, which is saying what does it look like in space at an instant in time. It's just a new example of a wave packet that's actually localized. And it actually localized in the sense that, yeah, it goes to 0 at x equals infinity, but it goes to 0 at its tail ends. So what does a Gaussian wave packet look like? So what this is this is an envelope term, and this is the oscillating term. So we have some amplitude A, and an envelope term and an oscillating term. So the first question is let's say, what is its maximum? You might say, oh, it's amplitude A. Well, let's make sure of that, right? What's the maximum of a cosine? The maximum of the cosine for any x is 1. The maximum of e to the minus constant, delta k is just a constant, right? K0 and delta k are constants. I didn't say that, but K0 is the average k, and delta k is the spread of k's. But anyway, they're just constants. And so what's the maximum of e to the minus x squared? Or e to the minus constant times x squared? the maximum is going to be when x is 0. So e to the 0 is 1. So indeed, this has a maximum amplitude of a and a minimum, or a maximum in the other direction, of minus a. And then the envelope term, which is e to the minus x squared, e to the minus x squared goes like this. I guess I should draw it in a different color. Make it, I don't know, orange. So the envelope term is like this. You can go ahead and graph it for yourself. And like this. Trying to draw. Sorry about wasting your time while I'm drawing this. Okay, so that's your envelope term. And then there's the oscillating term inside the envelope term. And I don't know what color I should make it. Let's go ahead and do this. So there's the oscillating term. I don't know if you can even see that, but it's fun to draw in silver. Okay, so that's your Gaussian wave packet. It is often used to represent a particle. It's the wave packet that might be used to represent a free particle. I think it's a free particle. I think so. Learn more about it when you get to quantum 1. And where it comes from and how it was come about. Okay, so that's an example of a wave packet representing a particle. The things that we're interested in is the localization of the wave packet, because the localization of the wave packet tells us about how much we can, how big the particle is, or really how much we can localize the particle, right? We can say where the particle is. So the localization of the wave packet. Now, since this, right, so it does indeed go to 0, at x equals plus or minus infinity. So to talk about the localization, what's the width of the wave packet? The way we talk about the width is often, there's different ways to talk about width, but is often what's called full width half maximum. So full width half maximum. What that means is if we take the maximum, a here, and we go to half the maximum, which is 1/2 of a, this is approximately 1/2 a, and we say, okay, what's the width? So I'm going to go ahead and draw, there we go. So this width here is called the full width half max, Fwhm equals, that is a measure of the localization. Oh, I forgot to write half a there. Okay, that's a measure of the localization. It is one way that we measure the localization of the wave packet. Because what if I asked, what's the full width? I mean, the full width is infinity, right? Because it doesn't go to 0 until x equals plus or minus infinity. That's why we got to do what's the full width at some particular limit. Okay, anyway, let's go ahead and calculate the full Fwhm for this Gaussian wave packet. So note that the envelope term, right, e to the minus delta k squared x squared, that's the thing that determines where the half max is, right? That at max is 1. So at half max is what? At half max. And that's what defines the half max. I mean, A defines the maximum value, but this is what defines the proportion of A as a function of X. So we say that, we could say that x0 is at max and x1, because it's a different x, x1. And actually there's going to be 2 x's at which it's half max, because this function goes like this, and so this is x1 and this is minus x1. All right, so if that's 1/2. So this is what we're calculating, is what are the positions x1 and minus x1 at which it's half max. So therefore, that, just take the natural log of both sides. There, you can solve for x1. Plug that into your calculator, natural log of 1/2. Square root of natural log of 1/2. And that's what you get for x1. So therefore, what's the width? The width is 2 times x1, right? That's just 2 times x1 because it's 0 here. So it goes from minus x1 to x1. So therefore, delta x, which is the width at half max, or the full width at half max, is 2 times that. So it's 1.66 over delta k. It's not plus or minus now because x1 was plus or minus, and that's what gave us delta x is 1.66 over delta k. So this is the full width at half max. And we can go one step further and say, okay, so delta k has to do with the spread of wave numbers of the wave functions that we've added together. So delta k has to do with that. It's not 0, it's not 1, it's just the spread. And we can actually rewrite this as delta x, delta k is equal to 1.66. And what that tells us is, depending on the wave numbers that we use, that this is that uncertainty relation we've discussed before. If we choose a limited delta k, if delta k is small, then delta x is big. It's going to make it a wider Gaussian function. But if we let delta k be a large range, a large delta k, then delta x is small, and we can localize it better. But this is that, remember that delta k is a measure of momentum because it's a measure of wavelength. It's a measure of momentum because it's a measure of wavelength. And so what this is that uncertainty relation that says we can't know both our velocity and our position at the same time. Because this is a measure of position and this is actually a measure of velocity. Can't know both our velocity and our position at the same time. We can know, if we know one better, we know one worse, because when we multiply how well we know the uncertainty in x times the uncertainty in momentum, you get a constant. Now, so that's the uncertainty relation. It's an important part of quantum mechanics, that you can't know both you can't know, there's various quantities which are, what's the word, when you can, if you know one, you can't know the other. Complementary, I think, that you can only know one or the other. If you know one, you don't know the other, or if you know one well, you don't know the other well, etc. So anyway, this is the uncertainty relation. And I do want to remind you that we've seen this before, and we've looked at this before, and we did it for the two, right, just for the psi equals psi 1 plus psi 2, when we had two single frequency wave functions. And for that, we found that the uncertainty relation was delta x, delta k is equal to 2 pi. We found for those wave functions. And you say, oh, wait, so for this particular wave function, the constant is bigger. For the Gaussian wave function, the constant's smaller. So maybe we can find a different wave function for which that constant's even smaller. Because the smaller that the constant is, the better we can know any one of these variables when we set the other one. So a smaller constant is good. And the Gaussian wave function, certainly 1.66, is smaller than 2 pi, which is 6.28. So we can localize our particle better with the Gaussian wave function than with the two component wave function. So then you say, so maybe there's some other kind of wave function other than the Gaussian wave function. And indeed, that's where we come to the Heisenberg uncertainty relationship. Heisenberg was able to show for a wave packet, and this is really important for quantum mechanics and for representing particles as waves, because they are waves when you look really close, is what Heisenberg was able to show is that there is a minimum. And what he was able to show is delta k, delta x is greater than or equal to 1/2. 1/2, 0.5, is the smallest for any wave packet you could possibly come up with. And he found that in 1927, and he actually won the Nobel Prize for that in 1932. So it's a pretty important fact that for any wave packet, this is true. You cannot come up with a wave packet for which delta k, delta x is less than 1/2. Do want to point that out, so let's go ahead and write that in terms of momentum. Because the de Broglie wavelength is essential here, is h over lambda, and k, this is k is 2 pi over lambda. Then we should be able to write that the momentum is 2 pi hk. Right? And 2 pi h, remember, is this h bar. That's why h bar is defined, because 2 pi h comes up so often, h bar k. And so therefore you can go ahead and say, okay, so therefore delta P is equal to h bar delta K. Go ahead and plug that in, and what you find is in the Heisenberg uncertainty relation that delta P delta X is greater than or equal to h bar over 2. And that is the position momentum relationship. That's this. Anyway, that's the localization that says, or that's the function that says, you see jokes about it all the time, can't know your velocity and your position at the same time. You can know them pretty close because h bar is a very small number, right? That's part of the point. That's part of the thing here is that this is only really appreciable effect when you're talking about subatomic. But you see cartoons and jokes about, here, I'll go ahead and find one. You got this one that you see a lot. This one. Pretty funny, haha. And then remember that one other thing is that we had also found a second uncertainty relationship, which was that delta omega delta t was equal to 2 pi for the two component wave function. And again, what Heisenberg found is that delta omega delta t is greater than or equal to 1/2. That's Heisenberg. And since E equals HF, which is, I just realized I put my 2 pi in the wrong place before. Hopefully you caught it. Here, this was h over 2 pi, which is, and it's h bar is defined as h over 2 pi, not 2 pi h. Whoops. Okay, come back. But this was still correct. This was still correct, and this is all still correct. Okay, come back to here. So we've got 2 pi over 2 pi hf. So that gives us h over 2 pi f, which is h bar times omega. So since E is equal to h bar omega, therefore we can see that delta E delta t is greater than or equal to h bar over 2. That's the Heisenberg uncertainty relation for energy and time. These are true physical limitations. They're not engineering limitations, right? They're true physical limitations that sort of like the speed of light that we just can't beat. Okay, that's all I got for Heisenberg uncertainty relationship. We're going to go ahead and finish up the chapter in the next day or two, and have a wonderful day.